Hey, what's up everybody, and welcome back to this Algorithmic Patterns course. So in this next part, we're going to go over an example problem that uses a dynamically sized window as opposed to our example from the previous part, which used a fixed size window. Unlike the problem from the last part, this problem is in the Leetcode patterns list, which you can find by filtering the list based on the pattern like so. The first thing that we're going to do for this problem is go over the question, because whoever wrote this question clearly deserves a Pulitzer Prize. And for those of you that are mere mortals like myself, don't feel bad if you can't begin to comprehend such masterful writing. And with that being said, we aren't going to even attempt to fathom what we're, let's face it, just not smart enough to understand. Secondly, for the way that we're going to visualize this, using fruits as the name of the input array is counterintuitive. So we're going to go ahead and change that input array variable name to trees like the mere pea-sized brain mortals that we are. Moral of the story, 50% of the difficulty of solving these Leetcode/hacker rank problems is being able to understand the award-winning writing that comprises the actual problem descriptions. In other words, the writing is shit. But once you can get over that hump, the rest is just being able to recognize and understand patterns. So let's start by trying to visualize what this problem is asking of us. Let's imagine we have a row or an array of trees. The problem literally says that the trees will be represented by an array called fruits, which doesn't make any sense, but I digress. So let's call the array trees. So this is our array of trees. Now let's imagine that we have two magical baskets. Each basket can hold an unlimited amount of fruit, but there's a catch. Each basket can only hold one type of fruit. And now let's imagine that there's a magical man holding those two baskets. Actually, there's nothing special about this man. He's actually quite limited, as he can only move from left to right, and he can't resist the urge to pick a fruit from a tree if he passes one. So this means that he must only move to the right, and he cannot pass a tree without picking a fruit from it. But there's a problem. This guy only has two baskets, and each basket can only hold one type of fruit, right? So what happens if this guy reaches a tree that produces a fruit type that he doesn't have a basket for? Well, at that point, the man can no longer pick fruit, so he would stop. Which would mean that, when starting from the first index of our array of trees, the man can only pick two fruits. So the objective of this problem is to figure out the maximum number of fruit that can be picked. The problem also mentions that we can start from any tree of our choice. So we just showed an example of how many can be picked if we were to start from the first tree of the array. So what happens if we start at the second tree? Well, let's have a look. So as you can see, we would be able to pick 4 fruits when starting from the second tree. And 4 is greater than 2, which is the number of fruits that we were able to pick when starting from the first tree. And when starting from the second tree, we were also able to pick from every tree leading up to the end of the array. So 4 is obviously the maximum number of fruits that we can pick for this particular array of trees. Now let's see how we can translate this visualization into a dynamically sized sliding window solution. So let's imagine that this array of trees is an array of integers with the tree type being represented as an integer. For example, let's have the tree that produces pears be type 1, the tree that produces oranges be type 2, and the tree that produces apples be type 3. So this array of trees would translate to an integer array that looks like this. Then let's start at our first tree with a window of size 1. Now we just need to expand the size of our window while strictly adhering to the constraints of the problem. That is, each contiguous element in our window must be one of 2 types. As long as we are adhering to these constraints, we can expand our window. As soon as we can no longer adhere to these constraints, we must stop the expansion of our window. And this is why this is a dynamically sized window as opposed to a fixed size window, because we're not getting any input that tells us the size of the window. we're actually going to be shrinking and expanding our window as we move through our array of trees. So since our window is currently only of size 1, we can add to some data structure a basket for this type of fruit. So we would now have a basket for the fruit type 1. But remember, we're allowed to have 2 baskets for 2 different types of fruit. So we can expand this window to include the next item and update our data structure to include a basket for this type of fruit as well. But at this point, we can no longer add additional basket types to our data structure. So the only way we can expand our window at this point is if the element or the tree that we are including in our window produces a fruit of one of the types that we already have baskets for. And we would expand until we eventually reach a tree that produces a fruit that we don't have a basket for. And once we get to this point, the number of fruits that we can pick when starting from the first tree is equal to the current window size, which is 2. We would then store that value to later be compared to following window sizes in order to get the maximum. And then at that point, we would update our baskets and shrink our window to only include the new fruit type and the previous fruit type that is adjacent to our new type, like so. And then we would continue with expanding and shrinking our window in the same way until we reach the end. So now that we understand what this problem is asking of us and how we need to implement our solution, let's get into writing some code. Okay, so just like in the last problem, I'm going to be using this YouTube patterns directory within my GoPaths source folder. And I've actually completely cleared out this directory in order to start with a fresh environment. And I'm going to create a file called fruitintobasket.go. And then I'm going to go ahead and open that file. And once again, I need to do go mod init. And then I can go back into the file. And we're just going to create the package main. And we're going to need to import format and math. From here, I can just create our main function just like we did with the previous problem, which is going to contain our input array called trees actually, which is going to be an array of integers. And I'll just go ahead and do an array literal here that contains the numbers from our example. And then we're going to set the variable answer equal to the result of fruit into basket. And we're going to pass in trees. We haven't created this function yet, but we're going to create it right now. And we want to print our answer. So now we can create the fruit into basket function. So we'll do func fruit into basket, and it's going to take in trees, which is an array of ints, and it's going to return an int. And to start, we'll just create a tree types map, which is going to be the data structure that contains our basket types. And we'll do map, and we're going to do int bool. So within the map, the integer is going to be the fruit type, and the bool is just going to be whether or not we have a basket for that particular fruit type. And you will see what I mean by this in just a bit. And then we'll do var max int, which is going to be the value that we return, the maximum number of fruits that we can pick. And we'll also do var start int. Just like in the last example, we're going to keep track of the start of the window and the end of the window. And yep, you guessed it, we're going to still do the same thing with the for loop using the end as our I. And we'll take tree type from range trees. So within this for loop here, this end is going to be the index of our trees array, and the tree type is actually going to be the value at that index. So that's how this for loop is working. And then we'll check if the length of the tree types map is less than 2, and if the tree types map does not contain the tree type that we are currently at, then we are going to add that tree type to our map. And after we do that, we're going to check to see if our max that we have stored is greater than or less than our current window size. So we'll do that by using math.max. And we're going to pass in float64 for our current max and float64 for our end minus start plus 1, which is basically the formula that we're going to use to get our current window size. And I'm going to go over this code step by step in just a second. So if you're not understanding anything, just hang in there. So if the above is not the case, and if our tree types map already contains the tree type that we're currently at, then that means that we can just add that fruit to our basket. So we would just go ahead and calculate our window size at that point. And we're actually going to do it the same way as above, so we'll just copy that. And if none of those two conditions are true, then we will go down to our else. So if none of those two conditions are true, then that means that we've arrived at a new fruit type, a tree that produces a new fruit type. So in that case, we need to completely reset our baskets. So we'll just do our tree types map is equal to, and we'll just make a new map of the same type as before. And then we're going to add the previous tree type that's adjacent to our new tree type to our map. So that's going to be tree n minus 1. And we'll set that equal to true. So this tree's n minus 1 is getting the tree type at our current index minus 1, which is the previous tree type. And again, you will see what I mean by this in a second. And then we're going to add to our tree types map the current tree type that we're on. And then we're going to set our start equal to end minus 1, which means that we're setting our start to the previous tree type that is adjacent to our new tree type, which I know is confusing, so just bear with me. And then we want to check to see if any previous tree types that were skipped when we set our start equal to n minus 1 are equal to our previous tree type that's adjacent to our new tree type. Because we want to make sure we're not leaving any trees behind that we have baskets for. So we'll do trees start equals trees start minus 1. And just think of this for here as a while. It's a while loop basically. So we're saying while the tree type at our current start is equal to the tree type at our current start minus 1. Then we're going to decrement our start, which is essentially going to go back and add those trees to our window. And this is the most confusing part in my opinion. So if you don't understand what I'm saying at this point, just wait until we get to the visualization portion in just a minute or two. And finally, we're going to once again calculate our max. And the last thing that we're going to do is we're going to return an int of our max. So we're going to convert our max to an int and return that. Now, I know this is very confusing, so let's get into trying to visualize this code. First, we can go ahead and run it. So go run. And as you see, we get 4, which is in line with our example from our presentation. So now let's get into visualizing this. Okay, so let's take some time to attempt to visualize what's happening within this code. So for this algorithm, we're going to be keeping track of a few things. We're going to be keeping track of our max, which is the maximum number of trees that we can pick fruit from, given our 2 baskets. We're going to be keeping track of our start, which is going to be the start of our window, which I will explain further in a second. And we're going to be keeping track of our end, which is going to be the end of our window, which I will also explain in a second. We're also going to be using a map data structure to keep track of our tree types. And this is going to represent our two baskets. And you will see what I mean by that in just a second. So first of all, to be clear, let's just go ahead and write these out. And we're going to have their starting values. So our start's going to start off as 0. And that's because in Go, when we declare a variable without initializing it with a value, it will be initialized as the 0 value for its type. So an int is going to be initialized as 0 if we don't initialize it with a value explicitly. So our start's going to be 0 and our max is also going to start off as 0. And all this code here is doing is creating an empty map, which is going to use integers as the key values and bools as the values. So for example, this map containing a value would look something like this. We would have the integer 1 for key, and it would have maybe the bool true for the value. And what we're going to do is we're going to have our tree types as integers, of course, because the input for the problem is going to be an array of, they call it fruits, but it's actually, in my opinion, an array of trees with particular fruit types, because integers are going to represent fruit types for this particular problem. And then we're just going to have a bool for the value to represent whether or not a particular fruit type exists within our map. And that's just for the purposes of making things a bit smoother when we write the code. And you'll see what I mean by that in a second. So we can go ahead and erase that. And we'll write our actual tree type map at the bottom here. And it's going to start off as empty. So we have our tree type map, our max value, and our start and our end. So now let's pretend for a second that this function is taking an input of trees, and that input of trees looks like this. So we'll have trees equals, and it's going to be an array containing 0, 1, 6, 6, 4, 4, 6. And let's throw the commas in there. So in this example, this is the input array to our function. And although the wording for the problem is a bit difficult to understand, basically what we need to do is we need to figure out the largest window size that we can expand to when each contiguous element can only be one of two types. So for example, let's say that our tree type map contains both 0 and 1. That means that we only can collect from these two types of trees. So we would start here and we would be able to collect from this type of tree, and then we would move on to here and we'd also be able to collect from this type of tree. But then when we get here, we only have baskets for type 0 and 1, so we wouldn't be able to collect this 6. So that means the window size for those two types of trees would only be of size 2. And following that, since we know that the elements within our window need to be contiguous, we know that we can remove this 0 type from our type map, because there would be no way for us to skip this 1 type here and still continue expanding our window with the 6. So what we would do is we would remove this 0 from our tree type map, and we would keep the 1 because it's still adjacent to this 6. And we would add this 6 type to our map. So we would then have type 1 and 6 in our map, and our window start would then be here. So we'd be able to pick from this type of tree, this type of tree, this type of tree, but then when we get to the 4, we would no longer be able to pick from this type of tree. So that means that our new max would become 3 because our window would be here, 1, 2, 3. So when we arrive at this 4, what we would want to do is we would want to remove this 1 from our tree type map, because we know that we can only have 2 types because we only have 2 baskets, correct? So if we're removing something from our type map, it would be the 1, because the 1 is not adjacent to the 4, and we need to add the 4 to our types. So we would need to move our start to this 6. So our window would start at this 6, and we'd be at this 4, and we know that we can pick from the type 4, so we would be able to pick from this next tree. And then we know that we can still pick from type 6, so we would also be able to pick from this last tree. So the final window would be from this 6 here to this 6 here, which would be 1, 2, 3, 4, 5 elements, which means our new max would equal 5, which would be the maximum size window. So let's go ahead and walk through this step by step. I know that it's a bit tricky to understand. Hopefully I can make things clear for you by actually stepping you through the code. So we're taking this trees array as our input, and this variable will be initialized as an empty map, and these two variables will be initialized as 0. And this for loop is the same as your standard for loop. We're going through the range of trees, and for this first variable here, this is the index of the element. And this second variable here is the actual value at that index. So that's how this for loop is working. We're able to get the index and the value. And the first thing that we're going to want to check is if the length of our map down here is less than 2. Because if it's not less than 2, then we're not going to be able to add another type to it. Because remember, we only have 2 baskets. And this map is what contains our 2 baskets. So if the length of our tree types map is less than 2 and our tree types map does not already contain the tree type that we're currently on, then we're going to simply add this tree type to our map. And we're going to add it by adding the key, which is the tree type, and adding the value, which is a bool, which is going to be true, meaning that it does exist within our map. And then here, we're going to set our max equal to whichever is greater, our current max or our window size. And the way that we're going to get our window size is by doing end minus start plus 1. That's going to give us our window size. So let me see if I can just write that out for you so that you can understand. So let's say that our indexes are here. And we have 0, 1, 2, 3, 4, 5, and 6. So these are our indexes. And let's say we have a window that goes from index 2 to index 5. To get the size of this window, which is 1, 2, 3, 4, the size of this window is 4. To get the size, we just would subtract start from our end and add 1. So our end is 5. And then we would subtract our start, which is 2. And then we would add 1. So 5 minus 2 is 3, plus 1 equals 4. And as you can see, the size of our window is 1, 2, 3, 4. There are 4 elements in this window. So that's what this end minus start plus 1 is doing. It's just getting the size of our window. So we can erase this, but we'll actually leave the indexes there. So what's happening here is our max variable is going to contain the largest window size. And we're going to continuously compare the size of our current window with our max. And we're going to store whichever one's larger, and that's how we're going to end up at the end of this function with the maximum size. So this is what's going to happen if the length of our tree types map is less than 2 and the type doesn't currently exist within our map. But if this is not the case, then we will move on to this one. We won't perform any of the code here. And this one just checks to see if the type already exists within our tree types map. And if that's the case, that means that we have a basket for this type. So that means that we can just go ahead and count the size of our window and compare it to our current max. And if it's larger than our current max, then we will make this our current max. But if not, we'll just keep the current max. And finally, we arrive at our else. If neither this or this is true, then that means that we've encountered a new type. And in that situation, we're just going to reset our map completely. We're going to remove all of the types from our map, and we're going to have an empty map. And then we're going to add the previous type, which is adjacent to our new type, to the map. And then we're going to add the new type to the map as well. So then we'll be left with 2 types, both of which are contiguous or adjacent to one another. And then we're going to set our start equal to our end minus 1, which is again going to be our previous type that's adjacent to our new type. And if that's confusing, just bear with me. I'm going to go over it in a second. And this last bit here is going to basically check to make sure our previous type that's adjacent to our new type has contiguous elements that are of the same type. Because here we're setting our start to end minus 1. So anything prior to this start will be left out. And if the element prior to this start is a type that we have a basket for, and it's contiguous with our current window, then we still want to keep track of it. So we're basically going to check to see if the elements prior to our new start are equal to one another. And if so, we're going to decrement our start so we can include them in the window. And I know that's very confusing right now, but I will go over it in just a bit. And finally, once again, we're going to just compare our max with our current window size, and whichever one is larger, we're going to keep track of that one. And once all is said and done, we're going to return our max. So let's get started with writing this out. So we're going to start the for loop at index 0, of course, with a value of 0. So let's write out our window currently. So currently, our start is here, and also our end is here as well. And we're going to check if the length of our map is less than 2, which it is, it's empty. And if the current type, which is 0, is already in our map, it's not. So we're going to add the current type, which is 0, to our map. So let's go ahead and add that. So we'll add key 0 is equal to true. And then we're going to get to this line here, and we're going to calculate our max. Our current max is 0 because we just started the for loop. And then we'll do end minus start plus 1. So 0 minus 0 plus 1 is equal to 1, which means the size of our window is 1 because our window is just this one element. So that means that our max is going to change to 1. And we're not going to do anything down here because this condition was true. So then we're just going to increment our end. Our end is going to go up 1. So we can erase that, and we can change our end to point to this 1. And we're going to check if the length is less than 2, which it is because we only have 1, so the length is 1. And we're going to check if 1 exists in here. It does not, so we're going to add it. So then we'll add 1, and then we'll add true. And this is why we're using bools here, by the way, because now we can just check it this way. We can just say, basically, if not tree types map tree type. So if this doesn't resolve to true, then we will execute the code in here. And for me, I think it's just more intuitive that way, but there's other ways that you can do this as well. So once we've added that 1 in this line, we're going to go ahead and recalculate our max again. We're going to check our current max, which is 1, and compare it to the current window size. And to make this more visual, we're going to use a line to represent our window. So our current window is here. This is our window. Our start and our end gives us our window. So to get our current window size, we're going to do end, which is index 1 minus 0 plus 1. So 1 minus 0 is 1, plus 1 is 2, which leaves us with our window size of 2. So our max is going to go up to 2. And once again, we're not going to do any of the code down here. We're going to end up back at the top of our for loop, and our end is going to increment. Our end is going to go up to index 2. So we can go ahead and erase that, and our end is now 2. So we're going to go ahead and extend our window. So now when we get to this part, we're going to check the length of our map, and our length is 2. The length of our map is now 2, so it's no longer less than 2. So this condition is not resolving to true, so we're not going to do any of this code. We're going to move down to here. So the value for index 2 is 6, which is the current type. We're going to check if the current type 6 exists within our tree type map, which it basically translates to, do we have a basket for the current type 6? And the answer is no, we don't. So we're not going to do this code. So basically that's as far as we can go with these two basket types, 0 and 1. So now we're just going to completely reset our baskets here. We're going to set our tree types map to a fresh, empty map. So we can go ahead and erase these. So now we have an empty tree types map, which means we don't have any baskets currently. And then we want to add back the basket that is adjacent to our new type. So our new type is 6, and that is at index 2, which is our end. We want to add back this basket type to our map. So we're going to do end minus 1, which is the index of the type that's adjacent to our new type. That's why it's end minus 1 here. So we're basically going to add back this 1 type to our map. So we'll do 1 and then true. And following that, we're going to add our new type as well, which is our current type, which is at index 2, which is 6. We're going to add type 6, and we're going to set it equal to true. And then we're going to set our start equal to end minus 1. So our end is 2. We want to set our start equal to here because we want to minimize the size of the window so that we're only keeping track of our 2 types. So we can go ahead and move that, and we can move this, and we can set our start equal to our end minus 1. So that's what we did here. And now here we want to check to see if any of the previous adjacent elements are equal to this type. Because if that's the case, we want those elements to still be part of the window. But if you look here, you see that 0 is not equal to the type of 1. So we're not going to do anything here. And again, once we get to a point where this is actually necessary, then you'll see how this is working. And then finally, we get here where we're going to check our current max, which is 2. We're going to compare it to our end minus start plus 1, which is our window size. And this window size is only 2, 1, 2, and our max is 2, so our max is just going to stay 2. So once we finish this code, we're going to go back to the top of our for loop, and our end is going to increment 1. So that means our window size is going to expand, and our end pointer is going to now be pointing to index 3. And we'll arrive here. Our tree types map is equal to 2, so we won't do that. And we will arrive here, and the value 6 at index 3, the tree type here at index 3, does exist within our tree type map. So we'll just calculate our new max by comparing the current window size, which is 1, 2, 3, to our max, which is 2. Which one is larger? This one is. So our new max is going to be equal to 3. So we'll go ahead and erase that, and we'll go ahead and set our new max to 3. And once again, we're back at the top of the for loop, and we're going to increment our end. So we'll go ahead and change the pointer to point 2, index 4, and we'll expand our window size. But the value 4 is not contained within our tree type map. So of course, we're not going to do this because tree type map length is equal to 2. And we're not going to do this because 4 does not exist within our tree type map. So then we move on to here, in which case we will reset our map to nothing once again. And then once again, we will re-add the type that's adjacent to our new type. So our new type is 4. We're going to re-add our 6 because end minus 1 is this index, which is 6, which we're going to re-add here. So we'll add 6 and then true. Sorry, maybe I'll just stick with blue, 6, and then true. And then we will arrive here and we'll add our new type, which is 4. So we'll go ahead and add 4 and then true. And then we're going to set our start equal to end minus 1. So end is index 4 minus 1, which is 3. So we're going to set our start to point to here. So we'll change this pointer to point here. But as you can see, our start is now pointing here, but we can also keep this in our window as well because it's of type 6, which is one of our baskets. And that's where this code comes in. We're going to check to see if this type here is equal to the type at its previous index. So we're going to do, this is a while loop, by the way, basically. This is basically while trees start equals trees start minus 1. So just think of this 4 as a while loop. This is basically goes equivalent to a while loop. So basically, while the value at our start is equal to the value at our start minus 1, then we're going to decrement our start. So 6 is equal to 6. So, oh, and I'm sorry, this is confusing because I didn't decrease the window. So the windows, so this is So this is our current window because our start is at index 3 and our end is at index 4. So this is our current window, but we want to include this in our window as well because it's still a type that's one of the baskets we contain. So we're going to check if this value is equal to the value at its previous index, which it is. And while that's true, we're going to decrement our start. So our start is 3 right now. We're going to set our start equal to 3 minus 1, which is going to be 2. So start minus minus just means start minus 1. So start is 3 minus 1 is now 2. So that means we're re-extending our window to include this guy. And then since this is a while loop, basically, we're going to do the same. We're going to compare this to this. And if this value or this type is equal to this type, then we would once again decrement our start. But this value is not equal to this type. So that means this loop is going to finish. So now our start has moved to include the other 6. So now this is our current window. So we didn't leave this 6 out, which is what this code is doing. So now we're going to get to here. We're going to check our window size. Our window size is 1, 2, 3, and our max is 3. So the max is just going to stay 3. Then we're going to get back to the top of our loop and we're going to increment our end. So our end is now equal to 5. And we're going to check to see if this type exists within our type map. Do we have a basket for this type? Yes, we do. So that means we're just going to increase the size because we have a basket for type 4. And of course we skipped over this because the length of our tree types map is equal to 2. So we check here to see if we have a basket for type 4, which we do. So we just compare the max to our current window size. The max is 3, our current window size is 1, 2, 3, 4. So our new max is going to become 4. And once again, we'll end up at the top of our loop and we're going to increment end once again. So we'll go ahead and change this pointer to point to this last element and we'll expand our window once again. So we're going to skip this, of course, and then we're going to check to see if our tree type, which is 6, exists within our tree type map. So do we have a basket for 6? Yes, we do. So we can just once again compare our current window size with our current max. Current max is 4, but our current window size is 1, 2, 3, 4, 5. So that means that this 4 is going to change to 5. And at this point, this is the last element in our array. So this loop is going to be finished. All of this will be finished and we'll end up at this return. We're going to return our max as an integer, which is going to be 5. So if this array is passed into our function here, what's going to be returned is 5, which is the correct output. Okay, so as a final note, let's go over the time and space requirements for this algorithm. So the space requirements for this algorithm are going to be constant because the space requirements won't scale with the size of the input. The tree types map is always going to be at max size 2, and we don't need to take any recursion or anything like that into consideration. So with that, we can just say that our space is constant, or big O of 1. And as for the actual time complexity, we're going to need to iterate through the entirety of our input array because our end is going to need to reach the end of our array. So that's going to leave us with big O of n, but we also need to take into consideration our start, and our start would, in the worst case, need to touch more or less the length of our entire array as well. For example, if we had a situation where we had an array that looked something like this, this code here would need to backtrack a relatively large portion of the array. So we can just say that in the worst case, both our start and our end would need to touch every element of our array. So the time complexity could be O of n plus n, which is the same thing as O of 2n. And in big O, we ignore constants, so this would equal O of n. So all in all, this algorithm would have a space complexity of O of 1 and a time complexity of O of n. And that's going to be it for this portion of this course. In the final two sections on the sliding window pattern, we will go over 2 additional problems from our Leetcode patterns list to solidify our understanding of this pattern.